So I throw an object in submerged underground water. The object A is hot. Well, what that means is Q lost by object A, the heat lost by that object is going to go into two places. This is kind of the purpose of calorimeter, not letting it get out to the world. So that heat energy goes into two places, the water and the calorimeter. The water and the calorimeter. So this is going to equal delta Q of the water plus delta Q of the calorimeter. That's the IB. And for every delta Q, we can substitute in mc delta T. Okay, we can substitute in mc delta T. So two methods, a direct method and an indirect method for measuring the specific heat of something. The direct method. I want to measure the specific heat of a liquid non-flammable. All right, not non-flammable here. Current 15 amps at 12 volts is put through the calorimeter to heat 230 milliliters of water in a calorimeter. And what is the change in temperature of the water? Now, specifically here, we would probably do this if we didn't know the specific heat of a liquid, because it's easier to measure temperature, right? You measure the temperature change, Q equals mc delta T, you can get the specific heat of that liquid. Here we already know what it is in water, so I want to find out what the temperature change is. Now, this concept comes out. Energy in equals delta Q of water plus the delta Q of the calorimeter. Does that make sense? I put X amount of energy in, specifically electrical energy, right? I put X amount of electrical energy in. And all of that energy goes into two places. It heats up the water, and it heats up the calorimeter. Now, this has a couple of flaws in it. This is assuming that everything's perfectly efficient, which it isn't, right? We're going to assume that. I need to give you a time. I forgot to give you a time. T equals 2.5 minutes. T equals 2.5 minutes. All right. Power. Let me work this derivation for you that we're going to need. And you've already seen something like that. What is the equation for power? Work over time, right? Or energy divided by time, right? Change in energy divided by time. You good with that idea? Now, on the IB problems that I gave you, I believe it was last Friday, I gave you another equation for electrical power. What was it? Does anyone remember? Current times voltage, okay, is electrical power. And this is topic 5, so we're going to get there. IB. This derivation is coming later. Okay, I just have to have it to work this problem. Okay. So what that means for electrical energy equals current times voltage times time, power time. Okay. It's energy, power time. I multiplied the time over to the other side. Power equals IB. Power also equals energy divided by time. So now I set up energy over time equals IB, current times voltage, and I multiply the time to the other side. I'm not looking for perfect understanding. I just need this to actually be able to work this problem. Okay? So I get this for electrical energy. Delta energy electric. IBT. Okay, now this sets me up where I can actually go somewhere. IBT. The electrical energy coming in, okay, current times voltage. Current is the amount of electrons actually going through, kind of like current of water. Just imagine the electrons in the water molecules. Voltage is the amount of force pushing. In America, what do we run at voltage, by the way? normally? If you stuck your finger in the outlet right now, how many volts are you going to get?
I was probably 120.
Okay. That's what's going to happen when you stick your finger in there. The tongue hurts worse. This becomes mc delta T, and this is all of my water, right? Plus mc delta T, and this is all of calorimeter. Are you okay with this? Yep. Okay. I stands for current, and V stands for voltage. So let's start plugging things in. I, current, 10.5 amps. V, voltage, 12 volts. T, current, T, time, 2.5 minutes. No light bounce. 150 seconds. I get to read. Yeah. Multiply by 60. 2 minutes, 120 seconds, right? Half a minute, 30 seconds. 150. Right, equals mass of water. What's my mass of water? 0.23 kilograms. Good. 1 milliliter equals 1 gram, right? I have 230 milliliters. That's 230 grams. That's 0.230 kilograms. Specific heat of water, 4.18 times 10 to the third. All right. Delta T. What is the change in temperature? That's what I'm looking for, right? Delta T of the water. Now, I've also got to tack on the calorimeter. The calorimeter absorbs heat. Okay. So I got to worry about that. So plus another mass of the calorimeter. Did I give you the mass of the calorimeter? Shoot. M, calorimeter. Calorimeters. 210 grams. Specific heat of the calorimeter. You have to know the specific heat of the calorimeter before you even get started here. Okay, so I set it at 10.7 times 10 to the second. Yes.
How would you know how to find the specific heat of the calorimeter?
Okay. You would either, now if you're doing an experiment here, it more than likely will be given to you. Okay, manufacturers manufacture those things at very specific numbers. So you can just flip it over to the bottom, look at it, look it up, and take a bunch of it. If you don't know, right? If you don't know that the specific heat of the calorimeter has to be what you're looking for, which you could do right here, this experiment. You can measure current, voltage, and time very easily. You don't know how to measure voltage and current yet, but ammeter, voltmeter, it just gives it to you directly. Piece K. Okay? Mass of water that you put in, specific heat of water, you know, right? And we could technically stick a thermometer in there and measure delta T, right? Change the temperature of the water. We good with that idea? You can mass out your calorimeter. C for the calorimeter is what you're looking for, and delta T for the calorimeter is the exact same thing as the delta T of the water. They should logically, assuming that there's not uneven heating going on, they should heat up at the same rate. They should heat up at the same rate. Does that make sense? Yeah? Okay? So you can measure the temperature, you can find the specific heat of the calorimeter. And that's a possible question at some point in time. Alright, now it's just algebra, right? So reducing down, someone multiply that entire left side for me, please. Say that again. 18,900 equals, I'm going to factor out my delta T And then, so that leaves me 0.230 times 4.18 10 to the third plus 0.2 times 10.7 10 to the second, and then my brackets here. Factor out delta T, right? Because it's different terms. Divide. We got ourselves an answer. And here, someone give me all that right hand stuff. That way we can simplify this down. 224. Okay, so add that divide over delta T. 15.9. Pretty Celsius.
Good morning, Morgan
There you
State
go.
High School. I need 6 following students up at the office, please. Morgan Sickle, Jeremy Kraft, Zachary Fossum, Shemaiah Grant,
Yes.
Christina Fitzpatrick, Martavius Jackson, Fred Williams, Ryan Williams, Jim Lacey,
Another question. And this is the other method. This is the indirect method.
Stefan
Okay.
Kitchen,
And this is actually what you're going to be doing for your lab, this idea right here, what you're going to be doing for your lab, I believe tomorrow. It might have to be Thursday, but we should hopefully get it in tomorrow. 250 gram piece of metal brought to 100 degrees Celsius by sticking it in boiling water. Now, if you put something in boiling water for long enough, right, boiling water has pretty much exactly, depending upon atmospheric conditions and what's in the water, a temperature of 100 degrees Celsius. You leave the metal in there for a long time while it's boiling, eventually it gets to 100 degrees Celsius also, right? Now, if you pull the metal out too quick, it won't have gotten up to the temperature. So you want to leave it in there for a while, okay? So 100 degrees Celsius, you pull it out of the hot water bath and you drop it in some water in a calorimeter, and you see what happens to the temperature, okay? What is the metal that must have been placed in the calorimeter? The way you can figure that out is by figuring out the specific heat of the metal. If you figure out the specific heat of the metal, you can go to a table and actually see what the metal actually is. Okay? So I'm going to give you, let me set it up and I'll let you go. Okay? So this is going to be, what's losing energy here? Metal. So negative Q of the metal equals what's gaining energy? Water and calorimeter. Good. Let me get my deltas in here. Delta Q of water plus delta Q of calorimeter. Trick here. The temperature change, the final
students, I'm
temperatures.
still looking for Zachary Fossum, Morgan Sickle, Jeremy Kraft, Shemaiah Grant, Christina Fitzpatrick, Martavius Jackson, Fred Williams, Ryan Williams, Jim Lacey, and Stefan Kitchen. Thank you.
The final temperatures of all these objects are going to be the same. Everybody got that? Final temperatures of all the objects are going to be the same. And the initial temperature of the water and the calorimeter is going to be the same, right? Which I listed at, let's make sure. Assume room temperature, 22 degrees. Okay? For the initial temperature of the water calorimeter. All right? Go for it.